Okay, hello everybody. Dear colleagues, I want to present you the talk on improving text-to-image models personalization on people with face-specific objectives. My colleague on this work is Andrey Filchenkov. So let's first of all start with the text-to-image models. And as previous speaker has already mentioned this topic, it all started like in 2021 with the DALL-E, but DALL-E didn't make that change in the field because it was like a wrapper around the GPT. But the next one, Glide, made a difference with the new techniques provided. And then in the previous year, in the 2022, we've seen a lot of astonishing results with the text-to-image generations and so on. And I think you all have seen this. For our work, we focus on the diffusion-based models and on the stable diffusion and especially in the diffusion on the stable diffusion, because it's open sourced, because it was trained on a large data set of the text to image pairs, of the text and image pairs. It uses open source clip as for the conditioning and processing images in a latent space. Here's the overview of the architecture, and it's pretty similar. It's pretty simple. We have then X batch of images. We encode it to the latent space from the pixel space, make a forward and reverse diffusion process involving conditioning on text or any other domain you want. And then we decode the latent representation to the pixel space and get the results. So what's personalization? Actually, there are a lot of models, diffusion-based models, which do these text-image tasks. But since they are trained on the large data set, which do not include every object you want to, object you want to generate, we may want to fine-tune it. And fine-tuning on a specific on a particular object or a style is called personalization. So for the personalization, there are a lot of different methods, and to the best of my knowledge, this is the full list of the fine-tuning methods for text-to-image models. They work in different ways, but we can divide them into the two groups. One is working only in the text space. The authors of those works state that the generators are already good enough so they can represent like any noise to the image. And we need to fine-tune only embeddings and so on. And on the other hand, there are methods that works in both text modality and visual modality. So what do we want from fine-tuning to what results do we want to get from the fine-tuning? Let's say we have an input samples like this for images of some statue, and we want to have an ability to generate this exact object in different excuse me, in different scenes, in different poses, in different contexts, with different backgrounds and so on, that were not presented in the initial data set that we provide for the fine-tuning. For example, well, we definitely have not provided this statue as an oil painting or an Elmo sitting in the same pose as this object. So this is exactly what we want from the fine-tuning on object. This method, textual inversion, works with the just embedding, so it optimizes only the newly created embedding for the object. The UNAD, the encoder, decoder, the textual encoder are all freezed, and they do not touch during the fine-tuning, so it's very fast. Next, aesthetic gradients. It works in a space of the clip embeddings, and actually during generation, it just moves the latent representation in the direction of some images we've chosen. Next, we have hyper. It's strongly related to connected with the textual inversion, but the difference is that hyper works with just a part of embedding, just 10% of embedding. It's interesting. Next, we have the Dream Booth, which is working in both text and image modalities. It fine-tunes and both text encoder, UNet, and everything that we have else on the generator side. If it's IM again, we have additional condition, super resolution blocks, and so on. So the results are quite like this. You have input images of a dog, and then you get a dog in different locations and contexts that were not provided in the initial dataset. Easy. Next, custom diffusion is like a fork of Dream Booth, but it works just with the key and value matrices in the cross attention, and you have some different, a little bit regularization. And also you can train different multiple objects at the same time. Next, we have encoder for tuning. The main idea here is to make a meta model for each class of images, like for dogs, cats, I don't know, people, and then do a fast fine tuning just in a little number of steps. Then the SUTI, the last method, it works a lot more complicated, but nevertheless, the main idea here is to fine-tune like 500,000 models on 500,000 objects, and then to train one big meta model SUTI, which takes an input images of your object, the prompt, and which is generating the object according to the prompt. So like this, without any fine-tuning, without any optimization, and so on, but with 500,000 models trained before. So I haven't shown the images from the LoRa because this method is initially provided for a different task, but community was able to apply this to this task. So if all those methods are here, why do we need to think about some different personalization on exactly people? The problem is that even if in general we can take any particular object like this chair here and fine-tune on this chair the model, unfortunately, when we speak about the complicated objects such as a human's face, the task becomes really hard in terms of getting the good results. Good results, by the good results, I mean the quality of the face, lack of artifacts, and the accurate identity of the person which we are fine-tuning on. So those are the problems. So the possible solution may be to look at the whole computer vision field before the text-to-image models, look at the face editing, the face swapping, head reenactment, and so on techniques, and to come up with the similar ideas and to take the idea of forcing the model to keep the facial identity and some features of the head, like because the identity is not just the face, it's also the shape of the head, it's also the hairstyle, and so on. So we want to keep it and want to force it. As our baseline, we use Dream Boost because in our experience, it is the best currently provided method alongside with the stable diffusion in the diffusion models field. So Dream Booth works as follows. We have a set of images On this slide, this is the set of images of a particular dog. Then we have the class of the subject, it's dog. Then we have the unique identifier of this object. Let's say this is just blah, 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 like 9 symbols or some rare token, and let's say it's blah, blah, blah. So as the text prompt, we use blah, blah, blah dog in the beach, or blah, blah, blah dog walking on a colorful carpet. The idea here is to choose the identifier which is rarely occurred in the initial training set. That's easy. So then we do some fine-tuning with Dream Boost and can generate our dog in different locations. But that's just the dog, and we're talking about people. So what do we have? What do we propose? We propose quite a similar approach, but with 2 additional losses. And here's it presented. First of all, we have a stage before the fine-tuning. We have the major problem of fine-tuning text-to-image models, large language models, and so on, large models. The problem is catastrophic forgetting and language drift. Those problems occur when you generate images of, let's say, different persons, males, after fine-tuning, and you understand that any man you see after fine-tuning is actually your object, your person that you trained on. So the model doesn't understand how different other men look like, but only your person. So first of all, with the fixed wrist model, we generate images of a man as our class. If we fine-tuning on a man, if we fine-tuning on a woman or on a different kind of person, we generate images of a woman or a person. We use it for a class-specific prior preservation loss. It's inherited from the Dream Boost paper itself. I'll describe later what do we want it for. Then we have input images, and since we want to preserve identity, we have to take this identity from the input images from the person. And for this, we have pretty good baseline. It's just an arc face model. It's just an embedding 1 by 512. It's baseline. Then on each step of the training, we generate by our fine-tuned model, we generate images of men and compare with the previously generated. By this, we force the model to keep in mind that there are different mens outside, different objects of the class. And on this, and along with this, we do a simple reconstruction loss. We do identity loss. So we compare the identity of the generated persons to the initial input set of images. And also we do multi-level feature loss, but I'll describe it later. So what do we have here? Let's say we have a batch of 2 images. And during the training, on each step of training, we choose 2 random time steps. We apply the random noise and random iteration for every single image we have in batch. And with our unit in the latent space, we have to predict the noise, which was initially applied to the image. Okay, so we predicted the noise, and with the reconstruction loss, it's everything that you had to do. But since we had a different losses, we have to denoise the image and compute the additional losses like identity loss and multi-features loss. So what are those losses? Reconstruction loss is when you simply doing some mean squared error between the noise and predicted noise. Class-specific prior preservation loss is when you do the same, but on the images of the class, like a man in our example. Identity loss is the cosine distance between the generated denoised images and the initial images from the dataset. And multi-levels feature loss, it's like a fit when you when you pass the image to the VGG or some another encoder and just get the values from the last layers and compare between them. And the last issue here is that we have a different number that on different stages of the noising, we have a really corrupted images and degraded images, and we just can't do identity preservation from these images because there is no face on them. Because of this, we need to weight additionally those losses with respect to the time step we have currently on. So briefly, discussions limitations. So if the face is small on the generated image, we have low signal, which may even not give an impact on training. Also, because of the feature matching loss, we can have a poor generalization. And conclusion, as you have mentioned, there's no results because the work is still in progress, but we have a conclusion. So as far as we know, we are the first ones to tackle this issue, and we propose a model agnostic in terms of a diffusion-based models and personalization approach agnostic method for improving text-image models personalization for people. Thank you. So I'm waiting for your questions.
Thank you very much for the talk, and we have some time for questions, so please.
Hi. Do you have some neural network which checks, secondly, your image is realistic or not?
No, we don't have one, but we can be sure if the image is realistic or not for now with the visual just perception, unfortunately. But also it's very hard actually to understand automatically whether the image is realistic or not. There are some approaches on how to do that. For example, you can label manually or not manually images with the label like this is 0 points of realistic, this is 10 points of realistic. I'll train some classifier and do this, but currently we are not in this stage.
Thank you.
Any more questions?
Thank you for the question.
So yeah, I have one, if nobody has else. So here we have condition, and I believe this is a brand new feature. So in this example, somebody could get that condition could be a man, a woman, and maybe if you are progressive enough, some more options. But what do you actually mean here? What could be conditions?
I don't mean that this is an additional condition. This is a regular text condition, which is passing to the conditioned unit through the cross-tension layers. And this in this specific step, which is generate images by the prompt man. Prompt of with the prompt of containing the class of the object person.
So, and what are types of classes of objects you consider?
We consider man, woman, and if you are progressive enough, there is person.
Okay, what about more or less? Okay, anyway, quite important features like let's say color of skin, ethnicity, some quite visually recognizable features which are quite important to keep.
Yeah, thank you. It's well, it's important to keep the diversity of the output images, and this is exactly about the problem with the catastrophic forgetting, because when we keep the diversity the same as before the fine-tuning, we can expect and be sure that the output of the model contain different people with different facial features and so on. But as the additional features to the input, like if we have this white, long-haired man with the beard, of course, we can use those features as an additional condition. But I think that this is not, first of all, we can do it. I think we can make an experiment of this, but me personally, I don't think that this is a necessary step, because the generator itself and the latent representation and the latent space are already good enough to capture any possible feature of a person.
Yeah, and actually, if we find that some features are lost, like for instance, red can be lost, if we have another angle, we can add it. Yeah.
Well, yeah,